Good evening, everyone. How many people have joined? Yeah. So this is basically the doubt session for the course on composites and polymers. This doubt session is mainly for the week 3 numericals. The theoretical questions will be answered in the forum. And right now we'll just solve the numericals in from week 3. That is question 5 to question 10. Please note that we are not giving you the entire solution in this meeting. We'll be giving you the approach and the hints that you'll be needing to solve the questions. So make sure you have a pen and paper ready to note down any useful points. Okay, let me share my screen. And any doubts that you have, you can put it in the chat, the YouTube live chat, and we'll try our best to answer your doubts. So first we'll go through all the questions in week 3, and then we can come to the doubts in the later half of the session. So starting, we'll look at question number 5 from week 3. Yeah. So the question states that a polymer based on Kelvin model is subjected to a constant load of 50 Newton with a cross-sectional area of 500 mm square of viscosity 10 Newton second per meter square and elasticity 1 meganewton per meter square. Find the strain response at time of 1 millisecond. So first of all, you have to see that it's a Kelvin model and it is subjected to a constant load, which indicates a creep behavior. So this is basically a Kelvin model subjected to a creep test. And the value of force and the area, mu and E are given. So this implies the creep load and it is based on Kelvin model. So we have to find the strain response from Kelvin plus creep. And as you might have seen in the lectures, this was derived by the professor. So the equation for Kelvin model under creep load, the strain response is given by this equation. So you have to simply plug in the values that are given in the question and you will find the answer. Now the sigma naught in this is basically the initial stress, and that you can find by using the force that is given and the cross-sectional area. So this is a pretty straightforward question, but the only challenge is that you have to identify that this is a question of a creep loading, basically. So if anyone has any doubts in this question, please put it in the chat box, or else we'll go forward to the next question. Okay, let's move forward for now. If there are any questions, we can come back. So the next question, a polymer specimen is stretched at t equal to 0 seconds such that the length is doubled. The elasticity of the polymer is 10 kilonewton per meter square and the viscosity is 10 Pascal second. If the polymer follows Maxwell model, what will be the stress response at t equal to 1 millisecond? Now, the first thing that you have to get, that this follows a Maxwell model, and it is stretched at t equal to 0. So that means that this is a relaxation test. Basically, the polymer is stretched at t equal to 0 seconds and held there. And it is given that the length is doubled, which indicates we can find the initial strain. And you have all the other values given to you. The E is given, mu is given, and you have to find the stress response. Now, as you might recall from the lecture, we find the stress response in case of a relaxation test. Sorry. So basically, instantaneous strain input at t equal to 0 is given. It is based on Maxwell model, and the stress response can be found out from Maxwell and relaxation. In the lecture, this was derived for a strain input at t equal to 0 seconds. And the equation is this, where the strain response is equal to sigma naught by mu into t plus sigma naught by E. So this is also a pretty straightforward question, just that you have to recognize that this is a Maxwell plus relaxation model. So if you plug in the values given in the question, you'll find the answer. So if anyone has any doubts in this, please put it in the chat box. I'll wait for a few seconds. Okay, let's move on to the next question. Now question 7. For a unit value of ratio of the applied stress and the elastic constant of the spring in a Kelvin model subjected to creep load, what is the strain response when time is equal to relaxation time? Now in this question, it is straightforward mentioned that this is a Kelvin model which is subjected to creep load, and the strain response is asked at a particular time. So as we saw in the question number 5, we saw the equation for Kelvin plus creep load. Now there's a line mentioned here for a unit value of the ratio of applied stress and the elastic constant of the spring. So this basically tells us that sigma naught by E, the value of this is given, which is unity. So since this is unity, the rest of the equation is just time dependent. And here it is given that the time is equal to the relaxation time. So if you substitute this in that equation, you can find the stress response, and you have to answer in percentage. Moving on to the next question. Question 8. In a 3-parameter based polymer model, the free spring has a stiffness of 250 kilonewton per meter square, and the spring in parallel with the damper has a stiffness of 150 kilonewton per meter square, while the damper has viscosity of 10 Pascal seconds. Now, in this, you have to recognize that basically this diagram is the 3-parameter model, and the free spring has a stiffness of 250. So basically, the value of E is 250, and the spring in parallel with the damper, which is this E1, the value of E1 is 150, and the damper viscosity is given as 10. Now you have to find the stress response of this polymer, which is subjected to a constant stress of 2 kilonewton. So basically, this is also a condition of a creep load. So stress is constant, and the strain response will be summation of the strains of spring and the strain due to the Kelvin model. But you can apply the equilibrium equations, like we know that the stress in the spring and the stress in this parallel configuration will be equal because they are both in series. the parallel and the spring. Basically, we can call this as one Kelvin model and one spring. So this Kelvin model and this spring is in series. So the stress in that will be equal. But the strain in that, which is basically the strain response, will be a summation of the spring, the strain due to spring and the strain due to the Kelvin model. Now, if you look at the equations, let's say sigma naught is the initial stress, and that will be equal in the spring and the Kelvin model. And the strain is the summation as we discussed. Now the strain in spring will be simply be sigma E by the spring constant, and sigma E is sigma naught. And we saw similar to the question 5 that the strain response for a Kelvin model under a constant stress, which is the creep load, is given by this equation. In this equation, the sigma E1 by mu, which is basically represents the stress in the Kelvin model, the total stress, this is also equal to sigma naught, as you can see here. So if you substitute this and add, we'll get the strain response up. And the tau here in this equation will be mu by E1 because it is based on the Kelvin model. So if anyone has any doubts, please go ahead and ask. Kartigan has mentioned we need stress response. I think you mean question number 6. Yes, we need a stress response in case of a relaxation test. We calculate the stress response because we are giving an initial strain and then the polymer is in that state, like the strain is constant. Then you calculate the stress response, how it will behave over time. If you have any other doubts, please put it in the chat box. Till then, let's move on to the next question. Okay. So in a 4-parameter based polymer model, the data for the springs and damper was given, and we had to find the strain response. Now, this is similar to what we did in the previous question. But here, a free damper is also there. So basically what we have to do is that we have to add the strain response of this damper to the 3-parameter model. Or you can do it completely from the scratch, like you have to add the strain response of this free spring, of the Kelvin model, and of the damper. Now this is similar to the question 8, but the strain response of damper is added. For a damper, we know that if the normal stress is equal to the viscosity into the strain rate. And if you have to find the strain rate, we have to integrate this equation. So by integrating, we find that strain for a damper, this is the strain response of a damper, that will be equal to sigma T by mu. And if you add this into the previous equation, which is the equation of the 3-parameter model, we'll get the strain response for this 4-parameter model, the complete strain response. So if you plug in the values that are given in the question, you can find the answer and match with the given range. So in this question, the main thing you have to notice is that since this is a series configuration of 3 separate entities, like one is spring, one is a Kelvin model, and one is a damper, you have to identify that to get a strain response, we have to add these strain responses individually. Since this is under a constant stress, as mentioned here, sigma. Yes, so if any doubts are there, please put it in the chat box. Okay. Carrying on to the last question of week 3. Now here, a V-chet model is considered with 2 maximal elements and a spring all in parallel configuration. Now in the question, there is no diagram given. So the main challenge is to identify that the diagram will be something like what it is shown here. Basically, we have two Maxwell elements in parallel. That is, one is this, second is this, and a spring. Now, if you don't add the spring in parallel, this will be basically a generalized Maxwell model with two elements. But since this is a V-chart model, we add a spring in parallel. Now, if you have to calculate the stress response of this relaxation test, so it is given that this is a relaxation test. Now, if this spring was not present, we can't actually perform. No, we can't perform. So this spring, sorry, so for this relaxation test, basically you have derived the equation of stress response for a generalized Maxwell model, and since this is a parallel configuration, we know that in the parallel configuration the stress are distributed among the various elements. So the total sigma here will be equal to the sigma here, here, and here. So sigma 1 plus sigma 2 plus sigma spring. So if we add the stress responses from each model, we'll get it. As you can see, the strains will be equal in the two elements in springs. Yes, so the stress will be divided, but the strains will be equal in all these elements. So epsilon spring will be equal to epsilon 1 is equal to epsilon 2. Now, alternatively, the stress response can be also be written as a summation of stress response of generalized Maxwell model and the stress response of a spring, as I mentioned earlier. So if we look at the equation, now for a generalized Maxwell model, this is the stress response. Now here, since we have two elements, the n is equal to 2. And the stress response of spring will be simply E into epsilon naught. So if you add these two, you'll get the total stress response. And since you have been given the values of all the springs and dampers, you can easily find the answer. Now note that whenever you're substituting the values in the equations, please take care of the units, because a lot of times you'll make mistakes just because of the units. Make sure all are in the same system. Like if you're using SI, please use SI for all. The time is given in milliseconds, please convert it to seconds. If the spring elastic constant is given in megapascals or kilonewton per meter square, convert it into meter per second square or pascals. That way, it would be easier for you to solve. So there's one doubt, or would you kindly provide the exact answers for the week 3 questions? It will also be helpful if you will provide the answers for all the full. Yes, so basically all the numerical answers are given in the answer section. But yes, we'll be providing some solutions. We'll be uploading it to probably NPTEL. But before that, we would like you to try this using this approach. And since you now have some clarity about this, the how to approach the question, I'm pretty sure you could get the answers. But nonetheless, we will provide you some solutions. Ashok says, I'm getting the value 480. Please mention the question number. And the range is quite wide, Ashok. It's 300 to 400. So if you recheck your calculations, I'm pretty sure you'll get some answers within the range. So yes, I think you're talking about question number 10. And yes, if you, I would like you to recheck your calculations, because yeah, the range is quite big, if you ask me. So I'm pretty sure you'll get the stress response. Make sure the time you've converted in seconds. If there is any other doubt, please put it in the chat box. Kartigan says mine was 364.75. Yes, that is similar to what is given in the range. What is the basic difference between Laplace domain and time domain? So basically, time domain is where you solve all the elastic problems. Time domain is the normal domain. And if you take the Laplace transform of that, you'll get the Laplace domain. So keeping in mind that you have your week 4 deadline tomorrow for assignment, and we received a lot of questions for week 3 numericals. So we decided we would give some basic hints for week 4 for the NATs, the numerical answer types. So let's get into some of the questions in week 4. Note that most of these questions have been covered by Prof. So if you refer to the slides, I'm pretty sure you'll be able to answer these questions. But nonetheless, let's get into it. So the question 5 says, consider an actually loaded polymer bar with a step input load as P is equal to 10 newtons, 10 H of T newtons. So the load is applied at T equal to 0. The area of cross section is given, length of the bar is given, and using Maxwell model with spring constant given and viscosity given, and using Alfred's correspondence principle, solve the given questions. Now you have to find the deflection. Now, if this was a question for a aluminum or a steel bar, this would have been a pretty easy question because then it would not show viscoelastic behavior, and this could simply be solved in the time domain. But since this is the viscoelastic bar, we have to use Alfred's correspondence principle. Now there are certain steps that you have to follow. Now, for Alfred's correspondence principle, the step number 1 is to solve the problem in the time domain for deflection. So you assume that this follows the principles that we use to solve any problem for steel or aluminum using the viscosity given, the spring constant and the elasticity given, and we solve it in the time domain. But we don't find the answer. We keep the variables as variables, and we find the equation in the time domain. Now, once you get the equations, let's say for delta, which I'm pretty sure you have all done solid mechanics to find delta for an actually loaded bar. Once you find that, you can replace all the variables by Laplace domain variables. And you replace all the elastic constant, that is the E, the elastic constant, that is the spring constant, by S times the Laplace domain elastic constants. So basically, if you have E of T, you replace this by S into E of S. And you maintain this as variables. And then you take the inverse Laplace transform. Now there's a slight hint that you have to use Boltzmann integral or the Boltzmann superposition principle that you've learned. If you do that, you'll find the answer. And after you take the inverse Laplace transform, then you can substitute the values that are given in the question. Yes, one major thing is after inverse transform, you have to use the Maxwell model for compliance or relaxation modulus, whichever is applicable. So once you take the Laplace transform, whatever you get, it might be compliance modulus or relaxation modulus, you have to use the Maxwell model for that. Now, if you want more clarity on this, please refer to the slides. It is mentioned very precisely by the professor on how to deal with the question after taking the Laplace transform. Meanwhile, let's see some doubts. Would you mind send me the solution? Yes, Ashok, the solution, I can't send it to you personally, but it will be uploaded to NPTEL and you can access it. And it will be the complete solution with all the answers. Yes, moving further. Question number 9 in week 4. Now, consider a viscoelastic prismatic bar simply supported under a point load, P0 at the center. Now, this basically a simply supported bar and you have P0. The length of the beam is L, area of cross section is A, elastic constant is E, and tau is the time constant. What will be the deflection at time T? And you have to consider the Kelvin model. Now, this is very similar to the question we've solved just now. You have to use the same thing. Now, you've been asked, what is the deflection? And if for a simply supported bar with a point load, I'm pretty sure many of you know what will be the deflection. It will bend something like this, and you can find the deflection in the time domain using the principles of solid mechanics. Now, if you have to find the same thing in the viscoelastic bar where the modulus is varying with time and temperature, you have to use Alphy's correspondence principle. So first you find the solution. The step 1 is finding the solution in the time domain, delta of t. Then second step, you replace all the variables by Laplace transform variables. Third step, you replace the elastic constant. Like I told you, E will become S times E of S. This is E of t. And the fourth step is inverse Laplace transform. And as I mentioned in the previous question, for the compliance or elastic modulus, this time you have to use the Kelvin model. So after taking the Laplace transform, you will get either an compliance modulus or elastic modulus. You have to use the Kelvin model. Moving on to the next question, which is the last question. Now, there is one more question in your week 4 question number, which I have not included in this PowerPoint presentation because the professor has covered this in the class. It is question number 6. This has been covered. This might be a doubt to many people, but if you refer to the slides, professor has covered this under viscoelastic bar under action loading. So if you refer to that, I'm pretty sure you can solve this question. Now coming to question number 10. Consider a stepped circular bar. Now there's a diagram given, something like this. Where the length is L1, D1, L2, D2. D1 is diameter, D2 is a diameter, respectively, and a torsional load is applied, T. Now, this bar is made of viscoelastic material with torsional rigidity as given as G of T. It is subjected to torsion whose value is given T naught H of T. And dg of T is the shear compliance modulus. Now you've been asked the theta. Now you might know from solid mechanics, obviously, since we are using Alphy's correspondence principle, we have to go to the step 1, which is solving this in the time domain. The only thing you have to recognize in this is that theta will be summation of the angular displacement in this bar and in this bar. Once you recognize this question is pretty straightforward. Basically, you apply Alfred's correspondence principles individually to the respective bars. You find the solution in time domain. You take the Laplace, you replace the variables by Laplace variables, replace the elastic constant by h times the Laplace constants, and then you take the inverse Laplace. Also, one more hint to this question is the prof has solved a question for not a step bar, just a normal circular bar under torsion. If you can apply that same constant, concept to this question, you'll get the answer pretty soon. So these are all the questions of week 4, which I have given a hint to. So it can help you solve. But yes, if anyone has any doubt in these numericals or how to approach or want me to repeat some questions from week 3 or week 4, please let me know. There were a lot of doubts from people regarding week 3 solutions. So I would like you all to try all these numericals once again with the approach shown in the PPT. And if you still can't get any answers, you can post it to the forum. Make sure you use the correct equation for the Maxwell and the Kelvin model. The equation which we get from the equilibrium and kinematics and constitutive relations, basically. This is in reference to one of the doubts that we had got in the forum. It was for Maxwell. The Maxwell stress response was asked, which was basically Maxwell plus relaxation. So one of the major mistakes is that you have to start. Now, of course, if you refer to the slides, there is a direct stress response been derived for this condition. But if you're considering Maxwell model and if you want to derive it by yourself from the scratch, you have to start from this equation. Which is the equation for a Maxwell model. Now, this equation is obviously derived from the equilibrium and the constitutive relations. If you use this, you'll get the right answer. Similarly, if you are dealing with Kelvin model, now this equation is not for Maxwell plus relaxation, it is just for Maxwell, not relaxation. And for Kelvin model, a similar equation was derived for stress response. Sorry, for the overall equation from equilibrium and the constitutive equations, that is sigma is equal to E epsilon plus mu into epsilon dot. So don't confuse between these two equations. This is for Kelvin and this is for Maxwell. Yes, if there are any other doubts on numericals, please let us know. We'll try our best to solve this. Kartigan has asked modulus changes along the deformation due to nonlinearity. Mostly plastic deformation is observed. Okay. Kartigan, how about you post this question to the forum so that we can discuss it with the prof and get back to you with more details. Since we don't have some questions on numericals, uh, and the week 3 assignment has the deadline has been passed, so let's discuss some of the initial questions. I'm pretty sure most of you have been able to solve this, but there were some doubts asked. So we'll look at it. Now, the first question was the creep response for a polymer following Maxwell model. So basically, here we are focusing on, let me erase this. Yeah, Maxwell plus creep. Yeah. Yes, Karthikeyan, you can see there's an ask a doubt section on the forum. Yeah, you can post any of your queries there. And if you're not able to answer right now, we'll definitely get back to you. Okay. So Maxwell plus creep. Yeah. So for a Maxwell plus creep, we have and for a, if we plot sigma and t, we have an constant stress input, right? What we solve for is the strain response. Yeah, there was a problem with Google Sheets. Apparently, a lot of people have faced this. So don't worry, you can post your questions here or on the forum. If there are many questions related to numericals again, we'll take another session. But for now, you can post it in the chat box or yeah, you can post it in the forum. But if there are any theoretical questions, it can be answered in the forum itself. So don't worry about it. As far as numericals is concerned, week 3 and week 4 are already covered in this session. So you might be able to solve the further weeks. Now, Just a second. Yeah. So the response of this will be something like this, which basically tells us there's an instantaneous strain. And as the creep is progressively applied, the strain will keep on increasing. So it approaches infinite equilibrium strain. So at t equal to infinity, the strain will be infinite. The next question is creep response for the Kelvin model. Now, if you look at the equation for Maxwell plus creep model, if I write the strain response equation, if you solve this, you get something like this. For those wondering where this line came from, this line, basically this is the equation of this line. Now for Kelvin model, we have this constant stress applied, sigma naught, and the strain response will be, if you look at the equation, it is 1 minus sigma naught by E into 1 minus E raised to minus T by tau. So if you plot this, what will be the graph? It will be zero instantaneous strain and it reaches a fixed equilibrium strain. Note that at t equal to infinity, this term will be zero. So it will approach a value of sigma naught by E at t equal to infinity. So it will be something like this. This is Kelvin plus creep. Are there any other questions? Yes, we'll keep the session open for 15 more minutes so that we can tend to any doubts. For anyone joining late, yeah, you can post your doubts in the chat box. Yes, anyone who is joining late can ask us question in the chat box. For anyone who missed the session, you can just go back and we've discussed week 3 and week 4 numericals. So, yes, you are welcome, Magarajan. I hope you all be able to solve the questions now. Uh, since we have no more questions, so since we have no more questions now, we'll end this session here. But make sure to go through this video and we'll upload the solutions soon for week 3. And week 4 and week 5 solutions will be uploaded later. But make sure you go through the PPT and the content that is put out by Prof, because most of your doubts will be solved in that. The important thing is that you read the question carefully and understand what kind of loading or what kind of model is asked and which equations to use, especially. Uh, Make sure that you know where to use Maxwell, where to use Kelvin, where to use creep, where to use relaxation test. And yes, if you have any more doubts, you can post it on the forum. Thank you everyone for joining. So let's end this session here.